This screen demo introduces important features of three-dimensional frame modeling by VisualFEA. Namely, procedures of constructing a three-dimensional frame, user interface for handling three-dimensional coordinates, representation of three-dimensional analysis data, and so on. To start the program, select New Item from the File menu. Project Setup dialog pops up for the setup of a new project. Click 3D Frame Radio button for a linear static analysis of a three-dimensional frame. Click OK button to complete the project setup. The modeling may be started from a few frame members, created simply by drawing straight lines. Each of the lines represents a structural member, with 2 end nodes. The view can be rotated easily by using the virtual trackball. The modeling space can be better visualized with the three-dimensional grid. A more complex model can be constructed by various operations with the initially created members. One type of modeling operation is duplication. The model can be augmented by duplicating all or a part of the initially created model. Choose Duplicate and move submenu item to duplicate selected members and place them at a specified offset distance. The Dupe and Move dialog has the items for inputting the offset distances in X, Y, and Z directions, and number of duplication sets. Let's select all members, and set the offset distance to 10, in Z direction, and number of duplication to 1. And press Duplicate button. Then, duplicated members are created at the distance of 10, in Z direction from the selected members. Another type of duplication is activated by Duplicate and Revolve submenu item. Dupe and Revolve dialog has the items specifying the angle of revolution and number of duplication sets. The dialog has 3 radio buttons for the options of defining the axis of revolution. Input option is to define the axis by creating a new line. Select option is to define the axis by selecting an existing line. Last option is to use the axis used in the last operation of duplication. This option is enabled only when there exist previously defined axes. Set the angle to 60 degrees and the number of duplication to 2. Select the members to duplicate, and click Set Object button. The button name is turned into Set Axis. Define the axis by inputting 2 endpoint using Input option. Now, Set Axis button is enabled. Click the button. 2 sets of duplicated members are created through revolution of 60-degree offsets. Let's turn off the grid, because it will not be used any longer. More members are added by connecting the nodes of the existing members. It should be noted that straight line button is pressed. Change the view direction, if necessary. And continue to add members. The geometry of a three-dimensional frame is completely defined. In the next step, let's define the material and sectional properties of the members. Choose Element Property item from Assign menu. The input items of the material properties include modulus of elasticity and Poisson's ratio. The sectional properties include section area, area moments of inertia, and torsional constant. The section items may be inputted, either by directly inserting the data values, or specifying the section shape and dimensions. For the latter case, click Edit button. Section Properties dialog pops up. One method of specifying the member section is to use one of the predefined geometric shapes such as circle, rectangle, T-shape, and so on. Let's use the default shape, that is, rectangle. Insert 0.2 for the width, and 1 for the height. The resulting cross-section is displayed on the right, with the section data, such as the section area, and area moment of inertia. The rectangle is made longish for this example in order to facilitate examining the orientation of cross-sections. The orientation implies the directions of the width and height, which are denoted by Z0 and Y0 respectively. Click OK button. Then, the computed section data are inserted automatically in the corresponding items of property dialog. Select all the members of the model, using rubber band selection. Click Assign button. Thus, all members are assumed to have an identical set of material and section properties. Choose Shaded Image item from Render menu, to obtain a shading image of the model. The image shows the orientation of the longish rectangular section for each of the frame members. The orientation is defined by the local coordinates of each member. One notable aspect of three-dimensional modeling, which makes it different from two-dimensional modeling, is the way of determining the local coordinates for each member. The user interface of VisualFEA for manipulating local coordinates is simple and intuitive. The directions of the local coordinates X, Y and Z can be displayed using Element Orientation submenu of Edit menu. Curve Selection button should be pressed prior to using this function. The local X-axes are displayed by choosing Local X sub-item. Likewise, local Y item to display the local Y-axis. And, local Z item to display the local Z-axis. The orientation of a member section is represented by the local coordinates of the member. The axial direction is always defined as the local X direction. The width and height of the section are measured in the local Y and Z directions, respectively. The local coordinates are initially determined for each member by the axial direction and the global coordinates. The local Y and Z directions are obtained using the equations of vector product shown on the screen. The initially determined local coordinates may deviate from the intended modeling. In order to solve this problem, VisualFEA provides a function to set the local coordinates. Let's display the top view of the model, which will be compared with the one after modifying the local coordinates. To start the function of setting the local coordinates, choose Local Coordinate Axis item from Assign menu. Local Axis dialog pops up. The local coordinates of each member are determined using the local axis in place of the global Y or Z axis. The local axis can be applied in three different arrangements: rectangular, radial, and spherical. The information about these arrangements can be obtained by clicking the question mark button on the right. The methods of defining the local axis are given in three options: input the axis, select the axis and as computed. The information about these methods can also be obtained by clicking the question mark button on the right. The local axis can be applied either in place of the global Z-axis or Y-axis. Let's take an example. Set the arrangement as rectangular. Set the method of defining axis as input the axis, and set the coordinate axis as Z-axis. Now, create a line by clicking 2 points. Click Set Axis button. Then, the newly created line is defined as the local axis, which will be used in place of the global Z-axis for vector product operation. Select the members to be assigned with the local axis. Let's select all members using rubber band selection. Click Assign button. There appears an error message, Unacceptable Local Axis Direction. This error occurs when there exist any members parallel to the local axis, for which the local coordinates cannot be determined by vector product. Therefore, such members should be excluded from the assignment. Let's deselect a member parallel to the local axis using Shift-click. Click Assign button. Then, the selected members are applied with the first set of the local axis. The shading image shows the altered orientation of the member sections. However, the orientation of the member sections for 3 purlin members are the same as before, because the newly designated Z-axis is identical to the initial local Z-axis of the members. The changed local coordinates can be identified by displaying the coordinate directions. In order to display the local X, Y and Z axes, check X axis, Y axis and Z axis items respectively. Let's use a different setting of local axis to lay down the orientation of the top purlin section. Press New button to create the second set of local axis. Set the method of defining axis as Select the axis. Select a vertical column. Click Set Z-axis button. Select the top purlin by clicking it. And press Assign button. The member is now applied with the second set of local axis, which is used in place of the global Z-axis for vector product operation. The shading image shows the changed orientation of the member section. In the next step, let's adjust the orientations of two purlin sections to the slope of the roof rafters. Press New button to create the third set. Set the coordinate axis option to Y-axis. Select the rafters on the left. Click Set Y-axis button. The local axis of the third set is completed. Select the left purlin, and press Assign button. So, the orientation of the purlin section is adjusted to the axial direction of the left rafter. Press New button to create the fourth set. Set the coordinate axis option to Y-axis. Select one of the purlins on the right. Click Set Y-axis button. The local axis of the fourth set is completed. Select the right purlin, and press Assign button. So, the orientation of the purlin section is adjusted to the axial direction of the right rafter. Let's take an example of using radial option for arrangement of local axis. Press New button, and click Radial Radio button. Top view of the model is displayed again for examination of the currently applied local coordinates. The rendered image suggests that the members shown in the upper part are not consistent with the members in the lower part. Therefore, the local coordinates of the members in the upper part will be adjusted using radial option. Radial option is appropriate for these members, because they were created by duplicate and revolve operation. Change the view direction using the virtual trackball for the convenience of defining and assigning the local axis. Let's change the method of defining the local axis to input the axis of radiation. Input two endpoints of the axis. First point is obtained by clicking the node at the apex, and the second point by inserting the coordinates. Click Set Axis of Radiation button. Then, the newly created line is defined as the axis of radiation, whose circumferential directions are to be used for vector product operation. Select the members using Shift-click. Press Assign button. Then, the local coordinates of the members are altered. Let's examine the top view again. The image indicates that the local Y and Z directions of the members should be reversed. Let's take the same procedure again with Y-axis option, instead of Z-axis. Clear the axis setting. Click Y-axis button. Input the axis of radiation, creating a vertical line from the apex point, in the same way as before. Click Set Axis of Radiation button to complete the modification of the fourth set. Select the members to change the sectional orientation. Press Assign button. Display the top view. Now, all members look consistent in their orientations. This completes adjusting the orientation of member section. Assigning the boundary conditions and load conditions are the remaining parts of the 3D frame modeling. Choose Boundary Condition item from Assign menu, to set the boundary constraints of the model. Boundary Condition dialog appears, and Node Selection button is automatically pressed. The dialog has the items of delta x, y, and z representing translational displacements, and theta x, y, and z representing rotational displacements. A displacement component is constrained, if its corresponding dialog box is checked, or free, otherwise. A fixed end condition is represented by the default setting with all 6 boxes checked. Let's assume the columns are fixed at their bottoms. Thus, select all the nodes at the bottom using Shift-click. And press Assign button. Choose Load Condition item from Assign menu to apply the external forces to the model. Load Condition dialog appears. Choose Uniformly Distributed from the drop-down list box, and choose Y direction item for force direction. Set the magnitude to -1. Select the roof part of the model, and press Assign button. The uniformly distributed forces are applied over the roof members. Now, modeling of a 3-dimensional frame is completed. The structural behavior of a frame model is represented most frequently in diagram forms. Let's recover the line drawing image of the model, which is more appropriate for display of diagrams. Use the diagram menu to display the analysis results in the form of diagram. Shear force Y item displays the diagram of the shear force in Y direction. The scale of the diagram can be adjusted using the slider control, which is obtained by Adjust Diagram Scale item. Likewise, shear force Z item displays the diagram of the shear force in Z direction. It is not always evident to construe the direction of the internal force from the diagrams. For this reason, the direction is visually represented on the model image, when the cursor is placed on the diagram. The direction of shear force is represented by a cube with 2 arrows. A yellow tip box shows the position and magnitude of the shear force. Following the movement of cursor, direction of the shear force and yellow tip box are instantly updated. Choose the bending moment Y item to display the diagram of bending moment about local Y-axis. Adjust the scale of bending moment diagram if necessary. The direction of bending moment is indicated by a cube with 2 curved arrows. At the same time, the yellow tip box shows the magnitude of the bending moment represented by the diagram at the cursor point. Choose the bending moment Z item to display the diagram of bending moment about local Z-axis. In case the diagram is obscured by many lines and texts, it is suggested to display the diagram only for selected members. Choose Diagram Display Options item from Diagram menu. Diagram Display Options dialog pops up. Check Show the diagrams on the selected members only item at the bottom, and click OK button. As you select a member, the diagram is displayed only for the member. Select another member by Shift-click. Then, diagram is also added for the newly selected member. Change the diagram item to bending moment Y. The diagram is redrawn for the switched item. However, the previous selection remains effective. The structural response can be expressed by contour image. Choose Contour item from Diagram menu. Contour Display dialog opens. Choose Combined Normal Stress item from the drop-down list, and click OK button. Then, the contour image is rendered. Here again, the contour is displayed only for the previously selected members. In order to obtain the contour image for all members, go back to Diagram Display Options and uncheck Show the diagrams on the selected members only item. Click OK button. All the members are rendered with contour image. The contour image is updated instantly when the frame model is modified. Let's modify the frame sections using Element Property dialog. Open the Element Property dialog again. Click New button to create the second set of Element Property. In order to change the shape of the cross-section, press Edit button of the dialog. Section Property dialog pops up. Let's choose the circular shape from the list. Set the radius of the circular section to 0.4. Click OK button. The section constants of the circular section are automatically inserted in the element property dialog. Press Curve Selection button and select the vertical columns. And click Assign button. The sections of vertical members are replaced by the circular section. The stress contour image is updated for the modified cross sections. Click New button to create the third set of element property, and click Edit button of the dialog. Choose I shape from the list. Insert the width, height, T1 and T2. As illustrated in the figure of I section. Now, the cross-section of I shape is defined, as specified, and drawn on the right. The section constants are also displayed. Click OK button. The third set of element property is completed with the specified I section. Press Curve Selection button and select the 3 purlins and click Assign button. Accordingly, I-shaped cross-section is applied to these members, and the stress contour image is updated. Magnify the contour image, using the zoom dial. Click a rafter member with rectangular section. There appears a small window, with the stress contour image, for the section at the point of mouse click. The contour image shows the rectangular section of the clicked member. Let's click a point on a vertical member with circular section. The contour image of circular section is displayed. Click a point on a purlin member with I section. The contour image shows the I section of the member. Drag the mouse with left button pressed. Then, the stress image is updated, continuously reflecting the stress of the cross section at the point of cursor. If you bring the cursor onto the section image, a yellow tick box shows the information of the stress at the point of cursor. This is the end of the screen demo for analysis of a three-dimensional frame using VisualFEA.